Uh, Good morning, students. I'm Vyom Sekhar Singh, and today I'll be taking up the revision of friction. Um to just sum up the chapter, friction is a particular kind of contact force. When two bodies are in contact, they interact with each other through the contact, and the force that they exert on each other, we call it contact force. There can be two components of this contact force. One would be along the common normal of the two surfaces. We call it normal. The other is along the common tangent, or that is perpendicular to the common normal, and that component of contact force is called friction. So I hope it is clear to all of you that friction is but a component of the contact forces between two bodies in contact. Yes, this contact force will not arise in all cases. There would be particular cases in which this contact force will arise. This contact force can have a certain nature, right? You know that there are two kinds of friction: kinetic friction and static friction. So in this chapter, basically, we study like what are the conditions for this tangential contact force or friction to arise, in which case it will be kinetic, and in which case it will be static, right? So those are the things that we are going to study here. There is also another kind of friction which we call rolling friction. I'll just touch upon it. It's not in the syllabus. You will study a little bit about it maybe in rotation, so that you can handle the qualitative questions, no numerical questions based on rolling friction. So for us, there are just two kind of frictions that we have to concentrate on: kinetic friction and static friction. So we'll start the lecture. I'm just starting the screen, right? Meanwhile, we can just keep on doing, right? So, what exactly is static friction? How is it different from kinetic friction? What are the conditions in which friction will arise? In which conditions friction will not arise? Right. So, those are things that obviously we'll be taking up in this chapter, right? Uh, okay. So what are the conditions that friction will arise, right? So if you think of it, there are two cases. One is okay. So friction, as we saw, friction is a tangential contact force which arises when two bodies are in contact, and right, there is relative motion or tendency of relative motion along the common tangent. Right, so friction arises when there is either relative motion or tendency of relative motion along the common tangent. Right, and of course there is one more condition. The condition is that the surface of the two bodies which are in contact, right, that surface must be rough, only then friction will act. Right, so friction is the tangential component of contact force, which arises if the surfaces in contact are rough and there is relative motion or tendency of relative motion along the common tangent. Out of this, if there is relative motion and because of that friction is acting, we call it kinetic friction. And if there is tendency of relative motion and because of that friction is acting, then we call it static friction. Right, so the most important concept in this chapter is basically to differentiate between the kinetic friction and static friction, to be able to decide when the friction is kinetic, when the friction is static. And it's actually very simple, right? You just need to stick to the basics, and you can get it very easily. So we move to kinetic friction first. So kinetic friction arises when there is relative motion between the surfaces in contact along the common tangent. Well, naturally the question is, what do we mean by relative motion in physics? Well, you know that the language of physics is math, so whatever definitions is before you, we must always be very clear about the mathematical equivalent. Every word has a mathematical interpretation in physics, otherwise obviously it is not relevant to physics, right? So what does relative motion mean? Does relative motion mean relative displacement, or does it mean relative velocity, or does it mean relative acceleration? Right, what exactly does it mean? So from now onwards, we must take it into account that whenever we say relative motion, we simply mean relative velocity. So relative motion, by this we mean relative velocity. Right, and now if there is relative velocity, there would be relative motion. Obviously it will lead to relative displacement over a finite interval of time, but it need not be equivalent to relative acceleration. So we can't say that if the relative acceleration between two surfaces is zero, then there is no relative motion between them. No, we can't say that. Or if the relative acceleration between two surfaces is non-zero, there is relative motion between them. No, we can't say this. We can only say that there is relative motion between two surfaces if there is relative velocity. So right now we are dealing with relative motion along the common tangent. So it means if there is relative velocity along the common tangent, then the friction is kinetic. Right, this friction is a constant force. Right, so and the value of this friction Fk stands for kinetic friction, is mu k into n, where mu k is called coefficient of kinetic friction. All of you are aware, right? It is a special constant which is a property of the two surfaces in contact, and n is the normal component of contact force between the two surfaces. N is normal component of contact force between these two surfaces, right? And mu k is coefficient of kinetic friction. So yeah, now what's the direction in which it acts? That's also very simple. It acts opposite to direction of relative velocity, or you can keep on saying relative motion. When we say relative motion, we simply mean relative velocity, right? Now if we move to static friction, we will obviously develop these points further using examples, but first let us just define the static friction first. So like you saw, a kinetic friction arises when there is relative motion, right? For static friction, the first thing we will write is that arises when there is no relative motion along common tangent. And so I hope it is clear, right? So relative motion or relative velocity has a very definite role to play. If v relative along common tangent is non-zero, the friction is kinetic. If v relative along the common tangent is 0, only then it is possible. I'm not saying that static friction will arise. There are more conditions to come, right? We say that only now it is possible that static friction may be present. If relative velocity is non-zero, the friction cannot be static. The friction has to be kinetic. I hope it is clear to all of you. I will repeat this because it's a very important point. V relative, whether it is zero or non-zero, is a very important fact in case of friction. If v relative is non-zero, no matter what the other conditions are, friction will be kinetic. And if v relative is zero, only then it is possible that friction can be static. I'm not saying friction will definitely come. I'm saying that friction may be static now. If v relative was non-zero, friction will be kinetic. It just can't be static. Okay, so we'll come to the other condition. Static friction arises when there is no relative motion along common tangent and there is tendency of relative motion along common tangent. So now the question arises, what exactly do we mean by tendency of relative motion, right? So again, you know that in physics every term has to be mathematical. So just like relative motion meant relative velocity, what do we mean by tendency of relative motion? So I'll write it because we are doing a revision. Otherwise, I would normally write it after the example. So we'll be able to understand this more clearly with the examples. But still, tendency of relative motion for us would mean tendency of relative motion implies relative acceleration along common tangent not equal to 0 if there was no friction, right? So so this is how it works, right? When I say what do we mean by relative motion, it means that v relative is non-zero. What do we mean by tendency of relative motion? It means that, well, A relative along the common tangent will be non-zero if there was no friction, right? So I'm not saying that the actual relative acceleration between the two surfaces is non-zero. I'm not saying that. I'm saying that the tendency of relative motion means relative acceleration along the common tangent would be non-zero if there was no friction. But now obviously there is friction, so I'll add it in bracket. But static friction ensures that a relative is actually zero, right? So just have a look here again, right? What do we mean by tendency of relative motion? We are saying that if there was no friction, then a relative would have been non-zero, but static friction arises and it ensures that a relative is actually zero. If you have this kind of case, then we say that there is tendency of relative motion, and this gives rise to a static friction, right? Now static friction, unlike the kinetic friction, which was a constant force, is not a constant force. So we'll write static friction is a self-adjusting force. So if you are having any difficulty in understanding these points, you have to just right, do your best, get whatever you can, and then wait for the illustrations, right? So the illustrations, I'll again come to these points, and I hope then you will be able to understand it clearly, right? So static friction is a self-adjusting force, right? So it adjusts itself on its own. Well, what will cause it to adjust itself? Well, we saw that earlier. Static friction ensures that a relative along the common tangent is actually zero. So to ensure that a relative is actually zero, there is a certain value of friction required, right? So that will be the value of static friction. So static friction will adjust itself in such a way that a relative along the common tangent is equal to zero. So we say static friction is a self-adjusting force, but subject to a maximum value, which we call limiting friction, right? So F limiting. So again, a very common doubt, that error that we have in mind, is that we think that limiting friction is same as static friction. It is not. What is limiting friction? Limiting friction is just the maximum possible value of a static friction, right? So static friction can have any value between 0 and limiting friction depending on the external conditions, because it has to adjust its value in such a way that the a relative along the common tangent is actually 0, right? So the value of this limiting friction is equal to mu s into n. Again, here n is the normal between the two surfaces in contact, or the normal component of contact force between the two surfaces, right? And mu s is again a constant of the two surfaces, right? It's a constant which depends on the nature of the two surfaces in contact. And in general, for any two given surfaces, you will find that mu s would be greater than mu k, slightly greater than mu k. Still, if in a problem the examiner has not specified mu k and mu s separately, then you can assume that he is assuming both of them to be same. So I hope I'm making myself clear here. Normally, for any surface, any given pair of surfaces, the static friction mu s will always be more than kinetic friction by a very small amount, right? But in numerical problems, very often we tend to ignore that difference, and we assume that both mu s and mu k is same as mu. So if nothing is specified, we will assume that both of them are mu, right? Whichever is given in the problem. If they are specified expressly, then obviously you know what mu s is and what mu k is. So even at the cost of multiple repetitions, I'll again at the end make one point clear. Kinetic friction is mu k into n, and static friction is mu s into n. Well, that is a big misconception we often carry in our minds. It's not like that. Kinetic friction is definitely mu k into n. It's a constant force. But static friction is not mu s into n. It's only the limiting friction or the maximum value of static friction, which is mu s into n. The actual value of static friction can be anything between 0 and mu s into n, depending on the situation. Right. So as I told you that we'll now move to illustration, and through that illustration we'll try to understand, because the whole chapter is about deciding where determining where friction will act, where friction will not act, where static friction will act, where kinetic friction will act. Okay. And okay, one last point, the direction of static friction. Right. So direction of fs, again I'll remind you, what was the direction of fk, what was the direction of kinetic friction? It was opposite to relative motion, that is opposite to v relative. So now direction of fs is opposite to tendency of relative motion. So what is it opposite to? So it is opposite to a relative if friction was absent. So this I have to write repeatedly, because actually the friction is present and it ensures that a relative is 0. But if there was no friction, there would have been a relative, and whatever the direction of that a relative, static friction will act opposite to it and ensure that a relative, the actual value of a relative, turns out to be 0. Right. So we'll just start with our first illustration for the day. Right. So example one. In example one, we'll take multiple cases. Right. So suppose I take the first case, and in all these examples, our aim is to determine the direction of friction and nature of friction. So maybe I'll write the question itself here. Determine the nature and direction of friction. Right. By nature, I mean whether friction is kinetic or whether it is static. So imagine that we have these two blocks, A and B, and let us say ground is smooth. Right. And the surface between A and B is rough. So since the ground is smooth, there can never be any friction between A and the ground. Right. So whether there is tendency of motion or not, whether there is relative motion or not, doesn't matter. But yes, between A and B there can be friction, and we have to determine whether that friction is kinetic, whether that friction is static. Right. And what's the direction of the friction? So let us say that the mass of B is 5 kilogram and the mass of A is 10 kilogram. So well, this data will remain same for the next series of cases we will be taking. Right, we'll be taking 4 or 5 cases. So in the first case, let us say that B is moving with a velocity of 5 meter per second and A is moving with a velocity of 10 meter per second. So in such questions, our first question is V relative equal to 0? Right, because whether friction is static or kinetic, it clearly depends on V relative. If we saw that if V relative is 0, then friction can be static. If V relative is non-zero, friction has to be kinetic. Right. So in this case, is V relative equal to 0? The answer obviously would be no. It means friction is kinetic. Right. Then what's the direction of the kinetic friction? Acting on B and acting on A. So again, suppose this is B and this is A. Right. You can see that with respect to B, A is moving forward. Velocity of A with respect to B is in forward direction, obviously 5 meter per second. And if I do velocity of B with respect to A, it will be in backward direction. So friction will act opposite to it. So this would be the direction of kinetic friction. Velocity of B with respect to A is going to be backward. Right. So if you have to see, This would be velocity of B with respect to A. It will be 5 meter per second in backward direction. So friction on it has to be in forward direction. This is Fk. Notice that these two frictions are action reaction pairs, right? So obviously they will be equal and opposite. And in this case, you know that it's kinetic friction, which is a constant force. So if mu k is known and you can find n, then you know Fk would simply be equal to mu k into n. Right. So let's move to the second part of the same example. Right. So we have the same bodies A and B having the same mass. Ground is rough. So all this data we are going to make it same. Right. So this is A and this is B. A is 10 kg. B is 5 kg. The ground is smooth. The surface between A and B is rough. Right. And now let us say that the velocity of B is 5 meter per second and the velocity of A is also 5 meter per second. And now imagine that there are some forces acting on it. Right. So maybe I'll just change color so that we can see the forces separately. So let us say that there is a force of 10 Newton acting on B, no such force acting on A. Right. Then now in this particular case, if you see further, the question is same, is V relative equal to 0? The answer is yes, which means that now friction cannot be kinetic, right? So no Fk. This conclusion we have already reached, but this is not sufficient to tell whether static friction will be present or not. For static friction to be present, there has to be acceleration if there was no friction. So we will draw the FBD of B and A. So this is B, A, and well, this is B, and we'll draw the FBD. The only force acting on B is 10 Newton, and I'm only showing the horizontal forces, I'm not showing the vertical forces. And since there is no friction between A and B, well, that is it. So is there acceleration of B? Yes. Acceleration of A is equal to 0. Acceleration of B is equal to 2 meter per second square. So well, acceleration of, now if I was to just show you the acceleration, you will see that acceleration of B with respect to A is in forward direction, or +2, or acceleration of A with respect to B would be in backward direction if friction was absent. So that was our criteria, right? Our criteria was that there should be no relative velocity, satisfied. In the absence of friction, A relative should be non-zero, again satisfied. So obviously here static friction will be present, right? And what would be the direction of static friction? The direction of static friction would be opposite to A relative. So on B it will act backward, static friction. On A it will act forward, static friction, right? So well, now there's one more condition, obviously, right? What's that condition? Static friction should be sufficient to ensure that there is no relative acceleration. So don't think that relative acceleration between them is actually 2. No, it will not be 2. If static friction is acting between them, the relative acceleration will be actually 0, right? Both A and B will have exactly the same accelerations. So now if I just draw the FBD again, right, the new FBD for B and A, taking all the forces into account. So B and A, for B there was a forward force of 10 Newton and there is a static friction acting backward. For A there is static friction acting in forward direction, right? And there is no relative acceleration between A and B. It means that both of them will have the same acceleration. Let us say the acceleration is A. So for both A and B, acceleration is A. If you have to find the value of A, right, you can obviously write separate equations for B and A, but we learned in the last lecture that what we will do is we'll try to do this whole thing in minimum number of unknowns. So we'll write equation for the system of A plus B. For the system of A plus B, friction would be an internal force. If friction is an internal force, the only external force is 10. That will be equal to mass of A, 10 kilogram, into acceleration of A, plus mass of B, which is 5 kilogram, into acceleration of b, which is also equal to a. So we got a is equal to 2 by 3 meter per second square. So the actual acceleration is not 2 for b and 0 for a, it's 2 by 3 for both of them. And then what's the value of static friction? So I'll draw only FBD of a, and you will see that static friction is the only force acting on it. It will be equal to mass of a into acceleration of a, that is equal to 20 by 3 Newton, right? So well, you know that all the conditions for static friction that we had enumerated, we have fulfilled them, right? First was no relative motion, so v relative is 0. Second was, in the absence of friction, the value of a relative has to be non-zero, which indeed is non-zero. The third is, once static friction acts, then a relative should be equal to 0. And the fourth condition is, of course, that this static friction has to be less than limiting friction, right? So what is the limiting friction in this case? In this case, you have limiting friction is equal to mu s into n, right? The normal between a and b is equal to 5g, that's 50 Newton. I am assuming g equal to 10, so that is equal to 50 into mu s. Now the value of mu s is not given to us. Maybe I'll put the value of mu s here, right? Let's say that mu s in this question is equal to 0.5. So if I put 0.5 mu s, then you can see here that that is equal to 25 Newton. So limiting friction is 25 Newton and the actual friction is 20 by 3 Newton. So is this actual friction Fs less than limiting friction? Yes, it means our assumption that the friction is static is correct, and indeed between A and B the friction is static. I hope it's clear to all of you, right? So we now move to the third case. Suppose again same data I'll use. 10 kg for A, 5 kg for B, mu s equal to 0.5, right? And here the surface is smooth, right? And maybe the force, the velocity here is now let us say 10 meter per second, and the velocity here is 5 meter per second, and then a force is acting, let us say, on A. Right, and let us say there is a 50 Newton force acting on it. So if you were to draw the FBD, right? So if you were to draw the FBD for this situation, you can clearly see that for B, apart from friction, there are no forces, and for A, there is a force of 50 Newton acting in forward direction, right? So here, like, you might be right. You can straight away see that since the force acting on A is forward, so the friction acting on A would be backward, and the friction acting on B would be forward, because the friction will oppose the force, right? This is a very common mistake we make, right? This entire thing is wrong, right? Because tell me, where did we learn that friction will act opposite to force? No, 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 we never learned that. We learned that friction can act opposite to either relative motion or tendency of relative motion. Neither of them is force, right? So just by looking at the force and determining the direction of friction is obviously a mistake. We will again have to follow the same process which we did in the previous two examples, right? So first I'll just remove these mistaken parts. So this F was a mistake, this one was a mistake, right? And well, this of course is 50 Newton, right? So we'll ask the same questions again. Is V relative equal to 0? And the answer is no. The moment you get this answer, you know the friction is kinetic, right? And if friction is kinetic, in which direction does it act? It acts opposite to V relative. You can see that it has nothing to do with the direction of force. It simply acts opposite to V relative, right? You can see in this case that velocity of B with respect to A is in forward direction, right? And that is obviously 5 meter per second. So obviously friction on B will act backward, kinetic friction, and friction on A will act forward. And this friction, kinetic friction, is a constant force. It's simply equal to mu into n, right? So if they have given that mu s is also same as mu k, which is 0.5, then it will be simply equal to 25 newton, the friction between A and B in this case, and the directions as we have shown here, right? So I hope it's clear to all of you that we will first not look at the forces. First we'll look at the velocities. Only if the relative velocity is 0, then we'll look at the forces. So that will bring us to the next example, right? So the fourth one, A, B. I'll use the same data again, 10 kg, 5 kg, and here mu I am using 0.5. I am saying mu, it means both mu k and mu is 0.5. This surface is smooth. Let us say A is moving with a velocity of 5 meter per second. B is moving with a velocity of 5 meter per second, and A is also moving with a velocity of 5 meter per second. And then let us show some forces acting on them. Let us say there is a force of 100 Newton acting on B, and there is a force of, let us say, 50 Newton acting on A. So these are the forces. So to solve the question, again, we have to follow the same process, right? First, we'll ask, is V relative equal to 0? The answer is yes. So now we know that friction may be present, right? So in what direction will friction act? So friction acts opposite to A relative if there was no friction. So we'll obviously draw the FBDs again for A and B, right? And the forces in the absence of friction in the horizontal direction are just these 50. So acceleration of B is 20 meter per second, and acceleration of A is 5 meter per second. You can see that BA, right? So the acceleration for B is going to be in forward direction with respect to A, 15 meter per second square. So here you have to be careful that these are not actual accelerations. These are just the imagined accelerations if we assume friction to be absent. So is A relative not equal to 0 in the absence of friction? Yes, it is not equal to 0. There is tendency of relative motion. So static friction will act. In which direction it will act? It will act opposite to A relative. So on B, it will act on B, it will act in backward direction, static friction. On A, it will act in forward direction, static friction, right? And to make it complete FBD, I'll show other forces also. The other force here is 100 Newton, and here the other force is 50 Newton. And we're assuming there is no relative motion between them. It means if acceleration of A is small a, acceleration of B is also small a in the same direction, right? Again, now if I want to write the equation to find the value of A, it would be best to write for this common system, because then Fs would be an internal force. The only external forces are 100 Newton plus 50 Newton is equal to mass of A into acceleration of A plus mass of B into acceleration of B, right? So this implies A is equal to 150 divided by 15, that is 10 meter per second square, right? And A relative is equal to 0. So neither the acceleration of A is equal to 15, nor the acceleration 20, nor the acceleration of A is equal to 5. Both of them have an acceleration of 10 meter per second square. But again, this is subject to one more condition, that the static friction should be less than limiting friction. So we'll find static friction. So this one was FBD of A plus B. Now let us draw the FBD of only A, and the forces acting are 50 plus F is equal to mass of A into acceleration of A. This implies A is equal to 10 if you put F is equal to 50 Newton. Right. So in this question, if limiting friction is more than 50 Newton or equal to 50 Newton, then the friction is static, and indeed the value of friction is equal to 50 Newton. But what's the value of mu here? Mu is 0.5 and normal is 50. So you know that F limiting is equal to only 25 Newton. This implies assumption of static friction or A relative equal to 0 in presence of friction is incorrect. Right. So the friction cannot be static because A relative cannot be ensured 0. You must understand that A relative is non-zero. It means the next moment V relative would become non-zero. Right. The next moment V relative not equal to 0, in which case, you know, friction is kinetic. So in this case, the actual frictions would be like this, A, B, right? So this was 100 Newton, the original force. This was 50 Newton, the original force. And this is kinetic friction, and this is kinetic friction. If they want you to find the acceleration, then you can find for B, you know, 100 minus F kinetic, which is equal to a constant force of 25 Newton, is equal to mass into acceleration. So it means that A is equal to 75 divided by 5, that is 15 meter per second square. And here you will have 50 plus 25 is equal to mass into acceleration. This implies A equal to 7.5 meter per second square. These are the actual accelerations of A and B. Right. So I hope you learned how to navigate between the cases when friction is static, when friction is kinetic. So friction kinetic is very simple. V relative not equal to 0, friction is kinetic. Friction is static, well, that is something which requires a lot of analysis. There are a lot of conditions for that. First is that V relative should be equal to 0. Second, in absence of friction, A relative should be non-zero. Third, in presence of friction, A relative should be 0. And fourth, the friction acting should be less than the limiting friction. If all these conditions are satisfied, then we will say that the friction is static. Right. So I hope now, what we talked about initially at the start of the lecture. Right. I'll move to that slide again. Right. So yeah, I hope it is now clear. Right. So kinetic friction arises when there is relative motion between two surfaces in contact along the common tangent. Right. Well, relative motion is nothing but relative velocity. And the second one, more important, static friction arises when there is no relative motion along common tangent. V relative is 0. And there is tendency of relative motion along common tangent. That is, in the absence of friction, A relative is non-zero. But static friction ensures that A relative is actually 0. And obviously, the last condition is that this static friction must be less than limiting friction. Right? Maybe I'll write here, F static must be less than F limiting. Right. This is the last conditions we have to check before concluding that the friction is static. So straight away now we move to the last topic of the day. Right. So we have understood about the uh, differentiation between kinetic friction and static friction, and we'll straight away move to two block problem. And this thing you can obviously generalize to three block problems or even n block problems, though they don't ask, they normally ask either only two block or three block problems. Right. So let's just move to two block problems. uh, Let me just tell you that the main frame of doing the two block problem we have already done. So to do the two block problem, you have to basically understand when friction would be static, when friction would be kinetic, especially when friction would be static, what are the conditions. So in two block problems, now it is A and B, right? I'll continue with the same data. This is 5 kg, and I think B is 10 kg, and let us say coefficient of friction here is mu equal to 0.5, and coefficient of friction here, I'm just doing an example, mu equal to uh, 0.1, and there are some forces acting on them, right? So this is let us say 100 Newton, and let us say this is 60 Newton, and question is find acceleration of A, B, find friction between them, etc. That's the question. So essentially the problem of two block problem, the main idea of two block problem is to first determine whether friction is static or friction is kinetic. That's the most important step, right? And there is absolutely no way in which you can determine it at the start of the problem. Like when we saw the previous two examples, let us think of the example 3, in which the friction turned out to be static, and example 4, where the friction turned out to be kinetic after all, right? So how do you determine? You can determine this only after the last step, right? First we assume friction to be static, we calculate the value of static friction, it comes out to be less than static limiting friction, our assumption is right. We assume friction to be static, calculate the value of static friction, and friction comes out to be more than limiting friction, it means our assumption is wrong. Actually, the friction is not static, friction is kinetic, right? So with that knowledge, we'll move to solve this question. So we'll do multi-block problem, 1 2 block, and we even do 1 3 block problem maybe, right? So now here, first step, we'll draw the FBDs of A and B, right? No velocities are shown here, so obviously we are assuming both A and B are initially at rest, so V relative is equal to 0, right? So is V relative equal to 0? What's the answer for this question? Yes. Why? The velocities of A and B are not shown in the problem, which means that both of them are 0, so V relative is 0. So now the forces for A, it is well, this one was 100 Newton, 100 Newton. For B, it is 60 Newton. Now well, how do you find the tendency of relative motion? Well, very simple. Assume that there is no friction, then these two are the only forces acting on them, right? So what's the acceleration of A? Acceleration of A would be 20 meter per second square towards right, and acceleration of B would be 6 meter per second square towards right. The only force acting on it is 60 Newton divided by its mass 10 kilogram, 6 meter per second square. Similarly, the only force acting on A is 100 Newton divided by 20 meter per, divided by 5 kilogram is 20 meter per second square. So is A relative not equal to 0? Yes, it's not equal to 0. So if you have to show the A relative, it will be this direction. Acceleration of A with respect to B is in forward direction, and in fact, if you want to find the value would be equal to 14 meter per second square. Let me tell you that these are not at all the final value. These are just assumed values if friction was absent, and friction is not absent actually here, right? So 14 meter per second square. So static friction, I'm assuming here, will act opposite to a relative backward, its reaction forward, Fs. So now if we draw the complete FBD, right? So I'll complete the FBD here itself. So okay, maybe I'll draw the next diagram, right, with the complete FBDs, let us say. So on A, this forward for 100 Newton and static friction backward. On B, the total force is 60 Newton. Sorry, not total force, the external force is 60 Newton, and static friction is also in forward direction. Now if you, and well, you know what's the third condition for static friction? That there is no relative acceleration, right? Friction acts in such a way that A relative along the common tangent is 0, so both of them will have the same acceleration A. Now again, if we write the equation for the combined system of A plus B, then the friction becomes an internal force. The only external forces are 100 Newton and 60 Newton, is equal to mass of A 5, acceleration of A, plus mass of B 10 into acceleration of B, right? So you have A is equal to 160 divided by 15. That is equal to, if you just divide by 5, it will be 32 divided by 3 meter per second squared. So this is the acceleration if friction was static, right? We have not finished yet. What do we need to check? We need to check whether the static friction here is less than limiting friction or not, right? So you know what is limiting friction here? Limiting friction is equal to 25 Newton. It's the same data as the previous problem, right? And how to find the static friction? Draw the FBD of only B or only A. So if I draw the FBD of only B, the forward forces are 60 plus Fs is equal to mass is 10 and acceleration is 32 divided by 3. So from here you can see that this implies Fs is equal to 320 by 3 minus 60, right? So 320 minus by 3 minus 60 would be 320 minus 180, that is 140 uh, divided by 3. Is it more than 25 Newton or less than 25 Newton? Obviously more than 25 Newton. So now you know that a static friction cannot be more than limiting friction. So it means that our assumption of static friction is incorrect. Right. So you know the next moment, which means that the irrelative will be non-zero. The next moment, v relative will be non-zero. Friction will become kinetic. Friction is kinetic. Okay. So well, A and B will draw the actual FBDs now. For A, the forward force is 100. The backward force is kinetic friction, which is 25. For B, the forward force is 60, and then kinetic friction. I think in this entire problem we have made one uh, major mistake, right? I had assumed the ground to be rough. We had to take it into account, right? And this whole thing I have solved by assuming that ground is smooth, right? So what I'll do is I'll go back and I'll change the data in the problem, right? And we'll do the next problem with ground rough, right? So we are assuming the ground is smooth. So that's the problem that we have been solving here, right? So ground we are assuming is smooth. So that's it. So you can find the acceleration for A is going to be 100 minus 25 is equal to 5 into A1, and for B it will be 60 plus 25 equal to 10 into A2. So we can get A1 and A2 from here, right? Straight away we'll move to the next example, right, where we'll take friction maybe at both the surfaces, right? So example 3 I'm taking. I'll change the data slightly, right? So A and B is 10 kg, B is 5 kg. Let us say that friction here I am putting as 0.8. Okay, no, I'll use a different value because there is one more misconception that we have very often. I'll take friction mu is equal to 1.4. We have this misconception in our head that friction has to be less than 1. No, there is no such condition. Coefficient of friction can be less than 1. Normally it is less than 1, but in many cases it can be even more than 1. So let's assume it is 1.4, and here I assume that mu is equal to 0.5, right? And suppose now we are solving the same problem. Okay, I'll put maybe the forces in the same vein. This is 100 Newton, and let us put a force here of, let us say uh, okay, 50 Newton. So that's the problem that we are solving now. So velocities are not mentioned. We will assume that the velocities are all 0. So v relative is equal to 0, right? So no kinetic friction. So we have to check for static friction. How do we check for static friction? Find the accelerations in the absence of friction. So we assume that there are no friction acting between A and B, right? Of course, I am assuming that A is moving. So we are assuming that there is going to be friction here. And if A is moving, this friction is going to be kinetic friction. And this kinetic friction would be equal to 0.5 into the normal here is 150. So that is 75 Newton. 75 Newton is the force acting here. And now this is B. So 50 Newton. And this one is, of course, 100 Newton. Right. So what is tendency of relative motion? We don't assume that all frictions are absent. No, we assume that friction between the two surface is absent, and in the absence of friction, A relative should be non-zero. So obviously you can see that now the acceleration for this body will come out to be 20 in forward direction. Acceleration for this body comes out to be 2.5 in backward direction. So acceleration of B with respect to A is forward direction 22.5. Again, these are not the actual values, these are just assumed values. So in the absence of friction, there is acceleration of B with respect to A along the common tangent. So static friction will arise, Fs, and here static friction in forward direction. And once static friction arises, then you know that A relative should be equal to 0. So we'll move to that condition again. So let's draw the final FBD with frictions, right? So B and A, the forward force is 100 Newton, and static friction, self-adjusting force backward, forward force is 50 Newton. The kinetic friction at the ground is equal to 75 Newton, and Fs acts in forward direction. So again, here if and both of them will have same acceleration because I'm assuming the friction between them is static, right? So if I take the system A plus B, then you can see that Fs is an internal force. It will just not appear in our equations. The forces acting are 100 plus 50 minus Fk, which is 75, is equal to mass of A into acceleration plus mass of B into acceleration of B. So you have 15A is equal to 150 minus 75, 75. So A is equal to 5 meter per second square. So this we have. And from here, if you need to find the value of static friction, just draw the FBD of B or just draw the FBD of A. So if I'm drawing the FBD of B, the two forces 100 forward and Fs backward. So 100 minus Fs is equal to mass into acceleration. So this implies Fs is equal to 75 Newton. Right. So Fs is equal to 75 Newton. Right. And what is the value of F limiting? F limiting is equal to mu s into n. Mu s we saw is 1.4 and normal was equal to 50. So that is equal to 70. So you can see that Fs actually comes out to be more than F limiting. So our assumption is wrong. Here, let me tell you that suppose instead of 1.4, I had given you a data of 1.6, let us say, then we would have got here 80 Newton. And so F is less than limiting friction. It means our assumption is right. Both of them have an acceleration of 5 meter per second square. That would have been the answer. But now it is just wrong. Our assumption is wrong because Fs cannot be more than 70 Newton. Right. So it means friction is kinetic. So we now will draw the last FBD with correct assumptions. A and B, this force was 100 and kinetic friction backward, and here this force is 50 and the kinetic friction at the ground is 75, and the kinetic friction is in forward direction, and this kinetic friction is equal to mu k into n. Mu k into n is equal to 70. This kinetic friction is equal to 70. So for B, you have 100 minus 70 is equal to 5 into A1. This implies the acceleration of B A1 is equal to 6 meter per second square. And for A, you have forward force 70 plus 50 minus backward 475 equal to mass is 10 and acceleration, let us say a2. So this you can see that 10 a2 is equal to 45. So a2 is equal to 4.5 meter per second square. So the actual accelerations in this case, for b it is 6 meter per second square, for a it is 4.5 meter per second square. So to sum up the two body problem, or the same concept you can use even for three body problem, is very simple. We cannot determine whether the friction is static or kinetic just by looking at the forces, right? You must do the analysis. And how does the analysis start? So we assume that friction is static. So for that, first we write all the forces apart from the friction between the two surfaces, find the assumed accelerations. If this assumed acceleration is non-zero, then static friction will arise to oppose it. And the static friction will not just oppose it, it will ensure that A relative is 0. Using this, we'll find the value of static friction. If it comes out to be less than the limiting friction, our assumption is obviously correct, right? The friction is indeed static. If it comes out to be more than limiting friction, it means our assumption is false. The friction is kinetic. Once friction is kinetic, you know the value of friction, you know the forces, you can go ahead and find the acceleration. So this would be the process. uh, let me again tell you that this process is nothing but solving the problem by trial and error. So if it's a 2-block problem, or it's a 3-block problem, or 4-block problem, we have to solve it by trial and error. We make an assumption, and you can work out to prove or disprove the assumption. If your assumption comes out to be correct, well, you have got the answer. If your assumption comes out to be incorrect, is still you now know that the friction is kinetic, and you know the actual values of friction. You can just do a little bit of calculation and get the actual accelerations, right? So thank you, right? I hope you will not be as fearful of the 2 and 3-block problems going forward. I would suggest that you can just go to HC Verma and do all the 2-block and 3-block problems there. So it has got quite a few number of collection of problems in this. So if you can just do them once again, I'm sure you will become confident in this. Thank you.